This is the first of a series of videos to help you to use the KINCALC program. KINCALC is an Excel program designed to analyze data from experiments with incubation robots developed by the NMBU Nitrogen Group. It has become an indispensable tool for our group, and I strongly recommend others to use it, unless you want to walk across the creek for water. It takes some time to grasp the structure of KINCALC and to use it efficiently. Thus these instruction videos. The present video is the first in a series that will enable you to get started. It gives a brief overview of the structure and instructions on how to import data and to put the right information into the spreadsheet. Before plunging into the spreadsheet, let me give you an overview of what it does. The point of departure is that you've done an experiment in the robot and you have exported the data using Excel Write. These data are then transferred to KINCALC, which sorts the data for you. Once you have calibrated the KINCALC, it calculates concentrations and rates of gas transformations, providing a platform for making instructive graphics, analyze enzyme kinetics, and explore regulatory phenotypes, etc., as illustrated in this graph. These calculations are based on the information and routines embedded in KINCALC. And these are the solubility of the various gases as dependent on temperature, the equation for transport of gas between headspace and liquid, splining routines for interpolating nitrite data, which will be explained later, calculation of rates, corrected for leaks and sampling loss, and calculation of electron flows to various terminal electron acceptors. Not the least, KINCALC is a useful packaging of essential information about each experiment. Each KINCALC file for each experiment contains original raw data, peak areas for each gas, material and method, that includes information about the organism, the medium, the temperature, the stirring rate, manipulations, etc., graphical presentation of the results, and the kinetic analysis, not only the results, but how they were done. This package is useful for the record, but also for discussions and refinement. The package can be sent as one piece for inspection by supervisor and colleagues, and can be uploaded as background information for publications. But this, however, requires something from you. And that means that you must secure that this KINCALC file contains the essential information about the experiment, which is not coming automatically. I will come back to this after a while. This is what I will go through in this video and what comes in the next. You can stop the video and read if you like. I will start with instructing how to import the data and what you must do. The raw data file that is produced by Excel Write program on the robot contains one sheet for each gas, 2 sheets for gases detected by 2 detectors, and your job is to copy and paste these data into the matching sheet in KINCALC. You may find that the names of the sheets in the raw data file do not match exactly with the names in KINCALC. This is not a problem as long as you get the right data in the right place. This is pretty straightforward, but there are a couple of important advices. Always use an untouched KINCALC sheet downloaded from our website or stored as a template in your own computer. Do not use one of your old ones, because you may have fiddled with it for legitimate reasons, but the changes may corrupt the analysis of the next data set. and it goes unnoticed. Next warning: never click and drag within the raw data sheet within KINCALC. It is destructive and you will have to start all over again. Now to the structure and function, simply how it all works. To do that, we will have to plunge into a spreadsheet. The case we are inspecting is a co-culture of two denitrifying strains. I will not go much into detail about the experiment, neither interpret the result, but simply use it as an example to show how things work. If you look at the bottom of the page, you'll see the different sheets named, and to the very left here you see the raw data files, one for each gas, CO2, N2O, measured by TCD, oxygen, neon, nitrogen. There's a lot of empty space here because we haven't measured it in this experiment. Anyway, so that's where you pasted all your raw data. Now to the very right, if you go to the number 1 and 2 and 3 and 4, you see the sheets for each individual vial. And we can start with the calculations and look at vial number 1. What these individual sheets do is to extract the data from the raw file and sort it so that we get the right data for each vial into its place. So now we have the raw data in the first columns here, and then in the next columns we have the concentrations, the calculated concentrations in micromole per microliter per liter, or ppm. If we go further to the right, we find two green columns, which are extremely important, but I will tell about those later. And then we go to the sheet for the different gases. Just ignore what's on top here, I'll come back to that. So for each of the gases, which are colored differently, we have two essential columns, which we will talk about today, and that is what we have in the vial: moles of oxygen in the entire vial, including the liquid, moles of NO in the entire vial, etc. Second column that I will talk about now is the rate. That is the rate of change, the oxygen consumption in this case, and the net NO consumption in this case, the net N2O production, net NO production, net N2O production, etc., etc. So we have essentially for each gas a core data set, and that is the total amount in the vial and the rate of change, what the organisms have been doing with this gas. To the left of the gas amounts and the rates, you find some pink columns, and that is the losses and leakage of the different gases. It is very important, but it's too early to talk about it. Further to the right, you find something called simple plot, which is a very useful table because it allows you to inspect to get an overview of the experiment. What you can do with this is to make a simple graph out of it by marking the area like this, and you insert an XY graph. Make sure that you include the titles so you get the titles in the graph, and here you are with the result. You have one graph for each gas. It's nitric oxide, it's oxygen. There is very little oxygen to begin with in this experiment, so denitrification starts right away, producing NO, producing N2, and producing very little N2O. There is some N2O, but you don't see it in this graph. If you want to see the N2O, you can reformat that one and place it on the secondary axis, and you see that you have an N2O peak here as well. So you can play around with the graphics here to get a more instructive figure. One of the other features of this, which is very important to understand, is that when you plot, what you get in the simple plot is this measured N2 in the vial. Now that starts from some value because we haven't been able to remove all the N2 before we started the experiment. We helium washed the vials, but it's not complete. So there is an initial amount of N2, and then it is increasing, and then it starts to decline again. What's happened here is that the organisms have used all the nitrate and nitrite at this point, and then the measured N2 starts to decline. Now, this is not very interesting to look at because it seems like something is consuming the nitrogen. However, further to the right, you see some other columns which are very interesting, and that is the cumulated production of N2, and if you want, cumulated production of N2O as well as CO2. What you can do, and it's more interesting to look at this one because this one is corrected for the sampling loss. This is simply the calculated cumulated N2 based on the rates. What we can do is to take this graph here, we mark N2, and we just drag it over to N2. You can keep the title as it is. Now you see you start at 0 and it reaches a stable level, meaning that the organism produces N2 until a certain point in time, and then there is no more N2 production. I would strongly recommend that you try to understand the calculations here, and that means that you should inspect the formulas. And if you look at the formula for cumulated N2, you see that it takes, if you look at this formula, it takes the previous value, which is 0 to begin with, plus AP27, and what is that? AP27 is marked over here. It's the rate of N2 production, 1.9 times 10 to the minus 7 moles of N2 per hour. And it adds that rate times the length of the time span between this measurement and the previous measurement. That's B27 minus B26. That's over here. And it multiplies this by 2 millions, because we want it in micromole N2N and not micromole N2 per vial. And when you propagate that cell downwards, you see that the next cell takes the previous and adds a new value. This is how we reached cumulated values. You will use this many times, and you will construct your own cumulated values many times, because it's a very useful exercise. If you look further to the right, you will find some columns where you are allowed to insert measured nitrite, and that is an exercise in itself to interpolate nitrite measurements, so we leave that aside for now. And then there are some various calculations, gross rates in each step of denitrification and the electron flow. We can leave it for now. It will be taken on in later versions of the later videos. And then we should go to the left again and try to show how these calculations are done, how this is parameterized. If you go to the top here, you find in column W a number of parameters that determine the response. that simply determines the first values here are the response factors for the different detectors, simply the ppm value per peak area, which is used to calculate the ppm values for each gas. There is another thing, and that is the temperature. You must set the temperature right and the pH right, and there is also an oxygen transport coefficient, which will be dealt with later. And then there is the sampling and leakage, which is also very important for calibrating your spreadsheet. The sampling volume, the oxygen leakage by injection, the N2 leakage by injection, and the septum leaks. If you look at these values, these parameter values here, you will notice, if you look at the formula, it is taking the values from the master sheet. And that's very important, that we have common parameters through all the experiment set by the master sheet, not in the individual sheets. There's also solubilities here, which are extremely important for the calculations, and that's all in the red area, and there are two red areas here, and that's a taboo area. Please don't fiddle with it, because there is a lot of calculations and factors in it that shouldn't be changed. So for each individual sheet, and they are all identical with respect to parameters and calculations, you see that they are identical, but the raw data are different. All these sheets take the values from the master. And what is the master sheet? You find the master sheet here, and that is an extremely important sheet, because it is really the master where you set all the parameters that should run through the entire experiment. Sheet also has another important feature, and that is that it can be used to inspect all the vials. You decide which vial number you will inspect by the value in B19. As you see here, I have the value number 1. That means that the data that I've plotted here, I have a plot from the result file, simple plot that I showed you previously, copied and pasted up to this place here. If I now change the number in this one, I import the data from vial number 2 into master. You can see that the raw data changes as I change these values. I go to number 3, I go to number 4, it goes slower and slower, and yeah, we don't have to look into the experiment, but the point is that this is a way to inspect the entire set of data and also to set the parameters for all the vials. One thing that you should put into the master vial right away is the temperature. Normally in all cases with normal robots, you run all the vials at the same temperature. The temperature is extremely important, because it determines not only the solubility of gases but also the molar volume of the gases. So to calculate the absolute amount, you have to get the temperature right. And you can see this if you watch the solubilities of the gases here, and you can even watch this one. If I now assume that I don't run this at 20 degrees, but I run it at 2 degrees, and I get completely different solubilities. The solubility of gases increases, and the amount of N2 accumulated is decreasing. This is all because the temperature determines mole volume, and it determines the solubility of the gases. Now to materials, which is another sheet. If you go down here, just beside the master, you find materials, and the materials is extremely important, and you must write all the experimental details that you need to remember to analyze your data, to understand your data, and into Adlib you can write on the right hand side here, you can write whatever you like, but make sure that you write enough. But the columns to the upper left are very important. In column B you write the names of the treatment in each vial. You have flask number, a vial number here, and you write the treatment name. And that name will be transported to the individual vials. So if we, for instance, look at vial number 8, we go to vial number 8, you'll see that it's treatment 0.75-0.25D. So it's important to have this in place. And the next thing that is extremely important is to write the correct amount of liquid in your vial. In column C, and you must, for the standard vials, remember to write 0. If you don't, if you fail to fill in this, it will all go wrong. These numbers here are also picked up by the individual vial sheets, so that if you look into, for instance, I have 3 standards at the bottom here, which are empty vials containing no liquid, but the volume is 120. And if you look into vial number 27, you see that the liquid volume is 0, and the total vial volume is still 120. So everything you write into material will be used. And you can also see that if I go to master again, and I want to inspect one of the standards, I go to 27. Now the gas kinetics looks quite funny. There's some noise here. But then you will see that the liquid volume is now 0 in this vial. And that's extremely important. You can't calibrate it adequately unless you know the volume in the, you have the right volume in the standard vials.